of Learning Plan 11, the second part, which is the heart. And this information comes out of chapter 18 in your book, so you can follow along. This chapter doesn't take a very long time to cover, so we're going to cover it in a relatively short span of time. So I'm just going to go over here and grab my PowerPoint, and then we'll get started. All right, so I don't really have to go into an explanation of where the heart is in the body. You probably knew that before you came in. But we want to talk a little bit about how the heart is set up. And I shouldn't say how the heart is set up, but the layers of the heart, the composition of the heart. And so if you look at this picture over here, we're showing you a picture of the heart, and we're kind of showing you where we're snagging a picture out of right here. So kind of where the blood vessel here called the pulmonary trunk comes off of the heart. So you can see its close proximity here. But right in here, this is the inside of the heart. And the inside layer of the heart is called the endocardium. And the endocardium is a layer of the heart that is really smooth, and it's non-stick. It's like Teflon. And it is actually continuous with another, well, I should say the inner layer of the blood vessel, which is called the endothelium. Basically the same type of tissue, non-stick, slippery, smooth, the whole 9 yards. All right, so that's the innermost layer of the heart. Then we have the middle layer of the heart, which is right here. And that middle layer is called the myocardium. The myocardium is a muscular layer. And the muscular layer obviously is responsible for the heart contracting, to squeeze the blood out of itself in order to move blood throughout various regions of the body. Then we finally have the outermost layer, which is called the epicardium. Now, this epicardium is actually continuous with the visceral layer of what we call the serous pericardium. If you remember the first day of class, the first lesson of class, we talked about serous membranes. And I told you to envision having a balloon in your hand. And you take that balloon and you take your other hand and you push your fist into that balloon. And I said the part of the balloon that's touching your hand, that's the parietal layer. That lines the body cavity. And then we also have the visceral layer, which would be the part of the balloon that's touching your fist. It's directly adhered to the organ itself, and that's why you see the visceral layer right here. Now, just like the balloon, the serous membranes are a sac, so you can actually see that sac will come and flip around. We got the other side of the sac, or the other side of the balloon, and that's going to be the parietal layer. And in between, we have a space, which is called the pericardial cavity, which is filled with a serous fluid, which is a very, very, very efficient lubricant. So essentially, you've got the heart surrounded by a sac of fluid, and this sac of fluid helps decrease the friction so that the heart isn't rubbing up against other structures within the body, because the heart beats 60 to 80 times per minute, and you don't want that kind of wear and tear on the heart. So here are the cardiac muscle bundles that surround the heart. And if you divide the heart into two areas, we have an upper region and we have a lower region, or a superior region and an inferior region. Either one works for me. And what we see is that the upper and lower contract at different times. So if the upper is contracted, then the lower is relaxed. And if the upper is relaxed, then the lower is contracted, okay? So this is what we see. And the reason why, because when the upper chambers are contracting, they're pushing the blood into the lower chambers. And then so when the lower chambers are relaxed, the blood can go in. Okay, then once the lower chamber starts to contract, it's going to push the blood out of the heart. And then when the upper chamber is relaxed, blood is going to enter the heart. So you're going to see that the heart will pump It'll contract top first, then bottom, then top, then bottom. Contract, relax, relax. And that's the way the heart operates. The heart is a very sophisticated, I shouldn't say not a very sophisticated structure, it's a very simple structure. But what's difficult is the act of reproducing it. If you try to find a replacement for a heart, a human heart is all that will do. And people have tried and tried and tried to create an artificial heart. Number one, it's hard to get it to fit in the same space, usually a little bit bigger. Number two, it doesn't run on its own. You have to have it hooked up to a device which extends outside of your body. So all of the artificial hearts that are available, I don't know how many there are now, but any artificial heart that you have is going to require you to carry around this device, drag it behind you, so it's not very portable. So you cannot get up and go anywhere, anytime. At the very best, you've got a backpack you have to wear in order for you to have that artificial heart. Third term is myocardium. Make sure you get that and grab that. Okay, this is a picture of the outside of the heart, the gross anatomy of the heart, the external structures of the heart. See a couple things. First, we see some blood vessels here, the two great veins, inferior vena cava and superior vena cava. Superior vena cava is going to bring blood from structures back to the heart, from structures above the heart. Inferior vena cava is going to bring blood back from structures below the heart. We have another large blood vessel right here. This is called the pulmonary trunk. This is blood leaving the right side of the heart, going to the lungs to get reoxygenated. And the pulmonary trunk is going to branch off into two different blood vessels called the pulmonary arteries. So we have a left pulmonary artery and we have a right pulmonary artery. The blood is going to return to the heart through the right and left pulmonary veins. See one here and one here. And then finally we have this large artery here, which is called the aorta, and the aorta distributes blood to the entire body. We also see these structures right here. These are called auricles, like the ears, and you have one on each atrium, and the atrium is the upper chamber of the heart. You have two upper chambers of the heart. Those are called atria. And the auricles are like these flaps, but they're there to allow for an increased amount of blood to enter the atrium. So if for some strange reason you get an unexpected increase in the amount of blood coming to the heart and you need an extra little bit of space or wiggle room, the auricles can fill up with a little bit of blood to kind of give you some more capacity. The other thing we see on this picture are some blood vessels. And we're going to go to the next slide. You'll see some more blood vessels. These are part of the coronary circulation. So people very loosely say phrases like, well, don't have a coronary. What they mean is don't have a heart attack. Don't get yourself so worked up. But the coronary circulation is very important. The coronary circulation is the circulation by which your heart feeds itself. Your heart does a great job of pumping blood to the tissues of the body so that they can get the oxygen and nutrients that they need. But the problem is the heart needs its own oxygen and nutrients. And the coronary circulation is the way by which the heart does this. However, these blood vessels aren't very well designed, in my opinion. It's one of the few places in your body that, man, for such an important organ, your body really got it wrong, in my opinion, because these are blind end arteries. So if you get a blockage of your artery, let's say right here, everything distal to that blockage is going to be deprived of oxygen and nutrients. It can die off. And if it does, that's a myocardial infarction, a heart attack. That tissue is dead. It won't come back. It won't work. So if you've ever heard of a bypass, what they'll do is they'll graft a blood vessel above and below the blockage, so that way the blood can make its way around the blockage, kind of like a detour, and continue to provide oxygen and nutrients to the heart. Take a look at the back side. You can see those vessels again, the superior vena cava here, inferior vena cava here. You can see the pulmonary veins coming back to the heart. You can see the pulmonary arteries leaving the heart. To the backside of the auricles, you can see some of the coronary circulation. Now, if we chop away the front of the heart, the anterior aspect of the heart, so we can see the inside of the heart, now we see 4 chambers. 1, 2, 3, 4. 4 chambers. The top 2 chambers are the atria. We have the right atrium and we have the left atrium. And then we have 2 chambers down here. We have the right ventricle and we have the left ventricle. So we track the direction in which blood flows through the heart. We start here with the vena cava. Blood returning from the upper structures or the lower structures, filling the right atrium. So number 1, blood enters the right atrium, passes through a valve called the tricuspid valve into the right ventricle. Once the blood is in the right ventricle, it's going to pass through another valve called the pulmonary valve, and it's going to pass out of the heart through the pulmonary trunk. And then it'll branch off into the right and left pulmonary arteries. If you want to add that as a step. Then the blood is going to re-enter the heart through the left and right pulmonary veins. Going to fill the left atrium. Going to pass through the mitral valve, which we'll talk about the valves in a little bit. And then it will enter the left ventricle. And then after it passes and comes into the left ventricle, the heart will push the blood through another valve called the aortic valve. And then the blood will pass through the aorta. I've got them all written here. So first, the right atrium. Then through the tricuspid valve to the right ventricle, then through the pulmonary valve to the pulmonary trunk, then the blood leaves through the right and left pulmonary arteries. Returns through the left and right pulmonary veins into the left atrium, passes through the mitral valve or the bicuspid valve into the left ventricle, then passes through the aortic valve into the aorta, and then it leaves the body. You'll notice here that on these valves, you've got these white structures here. They got little strings on them. And these little strings are called chordae tendineae. And the reason why they're there is because they're going to be pulling back on the valve so that the valve doesn't prolapse, so the valve doesn't move the opposite direction. You want the valves to open. In this case, both valves that we see, let me clear this off so you can see this a little bit better. Both these valves you want to open downward to allow the blood to pass through, downward, pass through. But what happens is when the ventricles contract, now the blood wants to go back through this, and you can't. You got to make sure those valves slam shut and don't let the blood pass back through. So these chordae tendineae pull back down on those valves to keep them from prolapsing. You don't want the valve to do this. You don't want the valve to prolapse and let the blood go back out. See? So sometimes people have issues with their mitral valve. Their mitral valve, they have mitral valve prolapse or an insufficient valve. So when this really thick, strong left ventricle wall squeezes this left ventricle, the blood wants to go back where it came from. And if that mitral valve is insufficient, then some of that blood is going to get put back into the left atrium, which is not what you want, because then that causes the left atrium to get weakened and enlarged and so forth. Not to mention it makes your left ventricle work even harder. All right, so that's what we've got. We've got that. So here are the valves again. If we're sitting in the seat of the atria, looking down into the heart, into the ventricles. These are the doorways to the ventricles, the tricuspid valve and the mitral valve. So they're going to open one way, and that's into the screen. But then we've got two valves coming back at us. We've got this valve right here. This is the aortic valve. This is going to open toward us. This is going to distribute blood through the aorta. And then we have the pulmonary valve. Blood that's passing through here is going to be passing through the pulmonary trunk and then going to the lungs for reoxygenation. Here's a picture of that chordae tendineae again. And what I didn't mention is that attached to the chordae tendineae are these muscles called papillary muscles. And papillary muscles basically contract to yank on those chordae tendineae, which then will yank on the valve to keep the valve from being insufficient or prolapsing. In case you need a reference to what I had mentioned before, figure 18.9 in your book does a great job of showing you the path of blood through the heart. So make sure you refer to that if need be. So when blood leaves the right side of the heart, it's going to pass through the pulmonary trunk into the pulmonary arteries, and it's going to travel what we call the pulmonary circuit. And the pulmonary circuit's job is to reoxygenate the blood. So you want to pick up oxygen from the lungs, you want to drop off the carbon dioxide because you want reoxygenated blood that will enter the left side of the heart, because it's the left side of the heart's job to distribute blood to the entire body. So the circuit that distributes blood to the entire body is called the systemic circuit. This is where the systemic tissues exist, and this is where gas exchange occurs. This is where we give the tissues the oxygen and nutrients that they need. And we will talk about these two different circuits next time when we come back and talk about the blood vessels. This picture does a great job of showing you the difference in the thickness of the wall of the left ventricle versus the wall of the right ventricle. And you can see the right ventricle wall is so much thinner. And the reason for that is because the right ventricle is pumping blood out through the pulmonary trunk into the lungs. And so the amount of resistance to flow, or the amount of back pressure that you're going to get from the lungs, is minimal compared to the amount of pressure that the left ventricle has to overcome in order to open up that aortic valve and push blood through the aorta. Requires a lot more pressure. And so the left ventricle has to contract a lot harder and much more strongly. So the left ventricle wall is much thicker than the right ventricle wall, as you can see here demonstrated in this picture. We already talked about the coronary circulation, so we're good with that. So that leaves us with this, and this will be the end of it. Looking at the cardiac muscle tissue. If you look at this picture, if you recall Learning Plan 4, when we talked about the different tissues of the body, one of the types of tissue was muscle tissue, and one of the three types of muscle tissue was cardiac muscle tissue. And you might recall that it was striated and had intercalated discs, and the cells were short and branched, and you're seeing that here. You see the intercalated discs, you see the short branched muscles here. So we see the striations, and so if you recall your skeletal muscle tissue anatomy, you'll see that we have the A bands and the I bands, the light and darkly appearing structures. You have the thick filaments, the thin filaments, the zone of overlap, M line, all that's the Z disc. You got all that. The only difference is the shape. Instead of being long and cylindrical, this muscle is short and branched. But we do see something that's very unique to cardiac muscle tissue, and those are these gap junctions. So if you recall, when we were talking about the nervous system, we had the nerve and the axon, and then we had the axon terminal. And when we passed it, we had action potential propagating along the neuron. When it got to the axon terminal would release neurotransmitter into the synaptic cleft. And then this neurotransmitter would have to bind to a ligand-gated channel that allowed sodium to pass through. And if enough sodium passed through this ligand-gated channel, the graded potential, enough to cause a change in the membrane potential from -70 to minus 55 millivolts, we get an action potential. And then boom, we're good to go. All right, well, when you're dealing with milliseconds, this takes a long time. It takes a long time to happen. And so if you waited for all your muscle cells of your heart to communicate this way, your heart would not contract as a unit, and it wouldn't contract as efficiently and as effectively as you would need to. So the heart has these gap junctions. And so the ions just directly pass right through them into the nearby tissue, or the cell next to it, I should say. And so you get the direct passage of ions from one cell to the other, causing a very rapid change in the membrane potential, which allows for a much more rapid action potential. This allows all the cells of the heart to contract as a unit. And this is very important because you need your entire atrium, for example, to contract at the same time. And then you need your ventricles to contract at the same time. And so the gap junctions allow for your heart to contract efficiently and effectively. All right, so that should be it. Go ahead and close this out. All right, so that should do it. So that covers the first half of Learning Plan 11 that we're going to cover today. Next time we come back, next week, we're going to be talking about Chapter 19, the blood vessels. Talking about the different types of blood vessels, the different type of circulation, introducing you to some of the blood vessel maps, so to speak, of the body. And then we're going to finish off with the lymphatic system, lymphoid organs and tissues as well. All right, thank you very much. Appreciate it. Take care. We'll see you next time.